Let us study the last part of numerical solution of the Navier-Stokes equations chapter. This part is called Ways to Improve the Numerical Method. When using the splitting of inviscid fluxes, the most good results are achieved when the modified Stigler-Wurman method is used. In this case, we use the following formula for the inviscid flux on the surface I plus 1/2. Here the matrices A plus and A minus are calculated using the middle meaning of vector u. But this approach is not suitable in the vicinity of strong shock waves. Close to shock waves, the method needs to be switched to the original Stigler-Wurman scheme, which is more dissipative. The Stigler-Wurman split is given by the following formula. The main difference is in calculating the coefficients A plus and A minus. The split Jacobins are evaluated using the state vectors UL and UR. To solve this problem, the following pressure switch method can be used. The flux, the inviscid flux, is calculated by the following formula. The coefficients A plus and A minus are calculated using the following formulas for U plus and U minus. U plus is equal to 1 minus Z U left plus Z U right, and U sub minus is equal to Z U left plus 1 minus Z U right, where Z is given by the following formula. That is equal 1/2 over 6 gamma plus 1/2 to the second power plus 1. The parameter gamma, which is given, which is presented in this formula, is determined by the normalized second difference of the pressure. You see that gamma is maximum value of values of E in different points, E minus 1, J minus 1, and so on. Where J, E E sub I j is given by the square root of 2e in to the second powers. And you see that we have the approximation of second differential, the absolute value of these differences. For small values of E, the parameter z is equal 1 minus z, and it's both equal to 1/2. And so modified Steger warming is recovered from the equation 371. You see that when z is equal to 1/2, we have the middle of UL and UR. Close to shock waves, the value of E is great, and so Z is equal to 0, because gamma is very big. And the method is switched to the original Steger-Warman scheme. You know that we have 3 types of approximation of left U and right R U. The first order upwind is given by the following formula. The second order upwind is given by this formula, and the third order is given by this formula. When we use first order approximations, we have a very robust solution. However, it has a significant error and blur shocks. Using second and third orders provides more correct solution, but with bucking failure at great pressure gradient. The simple extrapolation formula assumed a smooth variation of U, vector U. However, discontinuities in U are possible, that is, shocks. There is a need for some mechanism to sense such discontinuities and limit the variation of U in these extrapolation formulas. The following formulas for fluxes are suggested. UL, U from the left side, and vector U from the right side of the surface I plus 1/2. When phi is equal to 0, we have first order approximation. And when phi is equal to 0, we have the second order approximation when theta is equal to 1, or the third order approximation when theta is equal to 0. This member is 0, and this is 1. The following formula is for phi. Phi is maximum value of 0, and r, where r, here r, let's say, is equal to 1 over 6 gamma to the second power plus 1. In cases when pressure gradient is great, a numerical dissipation is added to the scheme. The engine values of Jacobians A plus, A minus, B plus, B minus, are calculated by the following formula, where, as you remember, lambda is the engine value of these Jacobians. Here E is supposed to be small number used only to correct the sonic glitched problem. In the current work, the parameter E is calculated by the formula, by the following formulas. For matrix A and for matrix B. The constants K1, K2 are set within the range from 1/2 to 2.5.